with alternating current, one advantage of using alternating current is that it's easy to transform the voltage from one value to another. So the object that transforms voltage of AC current is called a transformer. Transformer, the basic concept is just basically you have two coils of wire with differing numbers of turns. So the example here, I have 4 on one side, I think I have 7 on the other. You have those coils of wire wrapped around some kind of a core, usually magnetic material, where when the alternating current goes through this coil of wire, remember it's alternating, so the current increases and then decreases, it goes through 0, then it goes in the opposite direction. So the current is constantly changing. Because the current is constantly changing, the magnetic field that's created by the current is constantly changing. So the magnetic field in that coil of wire is constantly changing. That constantly changing magnetic field, shown here in the red, sets up magnetic field lines which pass through, that magnetic flux passes through the secondary coil. So you have a constantly changing magnetic field in the secondary coil. Since the magnetic field is constantly changing, the magnetic flux through this coil is constantly changing, which creates a current. So a current will develop in the secondary coil because of the changing current in the primary coil. But remember the EMF, right, the electromotive force for a current, for a changing magnetic field going through a circuit, depends upon the magnetic field strength, and it depends upon how the changing magnetic flux, which the flux depends on the magnetic field strength, the area, and how quickly the flux is changing. The angle between the magnetic field and the loop of wire. So here we have a constantly changing magnetic flux which generates current in the secondary. By changing the number of loops, you change the potential generated at both sides. So here you have some voltage from the primary. This is the alternating current going to the transformer. You have the voltage in the secondary. This is the circuit coming out of the transformer. At no place do these wires touch one another. One induces current into the other. And you can then step up or step down the voltage on this device, or using this device. This is incredibly handy because alternating current, as we talked about much earlier, is a better, more efficient means of transporting energy than direct current is. Direct current, again, where the potential stays at one level, that type of current, if you try to push it over very long distances, you lose a lot of the energy. So unless you build power plants, a lot of them very close to cities and many in the city itself, the voltages will drop dramatically and the energy will be lost if you have to transport energy a long distance using DC current. Alternating current is far more efficient. You still lose 20 to 30% of the energy when you transport alternating current over regular copper wires, the big, thick, high voltage wires that can travel for hundreds of miles from a power supply, like a dam, a hydroelectric dam, or a nuclear power plant to where the energy needs to go. But alternating current delivers more of the power. It loses less energy. And alternating current works best at high voltage. So the lower the voltage, the more energy that's lost when you're transporting electricity over a wire. So you want to transport it at very high voltage. So the power lines that you see running to and from cities, the big power towers, right, where you have many, many multiple lines running across, not just the low power lines that you see in a neighborhood, but the high voltage lines you see near a power generator or a power plant. These are almost always at very high voltage, 10,000 volts or so, and you'll see danger warning signs written all over these power lines, these towers that hold these power lines, because you want to transport this energy at high voltage to get it to where it needs to go. But you don't want 10,000 volts coming into your home. That voltage can easily kill. So while you step up the voltage to transport it, once you get it to where it needs to go, you can step down the voltage to make it more safe. So the power lines that run through neighborhood might be 700 volts, 1,000 volts or so. And then transformers step that down to 110 volts, 120 volts when it's delivered to your house. So you can get then the voltage of the house, you can get 110 volt circuits. 220 volt circuits, you can get wiring where some of your electric appliances require 220 volts. And then there's a way to do that in the circuit breaker box to double the voltage basically. But also encourage, if you want to know how to step up or step down, it's just a simple ratio of the number of wraps, the number of turns on each side of the coil. So the ratio for the voltage in the secondary compared to the voltage in the primary is equal to the number of coils in the secondary versus the number of coils in the primary. So if this secondary has twice as many coils, the voltage coming out is twice as high. If it has 10 times as many coils, it's 10 times as high. If it has 1/10 the coils compared to the primary, the voltage drops by a factor of 10, right? Which 1/10 as big. Now, while the voltage is stepped up, the current actually is stepped down, right? Power is equal to current times voltage. P equals IV. We learned about that when we talked about electricity. Well, conservation of energy states that you can't just magically make energy out of something. So if you're delivering a certain amount of power, energy per unit of time, and you increase the voltage of that source, the current has to diminish by equal amount. So if you increase the voltage by a factor of 10, the current's going to drop by a factor of 10. If you increase it by a factor of 5, the current will drop by a factor of 5. So while the voltage will get stepped up, you can see that the current, the ratio of the secondary to primary currents, the ratio of the numbers here flip. So if you step up the voltage, you step down the current. If you step down the voltage, you step up the current for these types of transformers. Now, transformers are not 100% efficient. Again, here's the electrical symbol for a transformer. 2 coils of wire around some core, between them. Transformers aren't 100% efficient. You don't want to transform power up, step up and step down a lot because you lose a little bit of the power in this process. Not all the magnetic flux goes from one coil to another. You do lose a little bit of efficiency. These transformers can heat up, especially if you're drawing a lot of power. Transformers can blow. There are transformer boxes in those, basically not telephone poles, but the electrical poles. Those transformers can explode. They do heat up quite a bit. You can have some dangerous situations with transformers. But overall, transformers are incredibly useful to the American and not just American, worldwide electrical system because it allows us to step up the voltage to transmit electricity at more efficient, high voltage, low current to get more power to the destination, more energy, less energy loss to the destination. So this is how a basic transformer works.